Welcome to my channel and welcome back. And this is Dora. And in this series, I will show you how to simulate uh, a semi-submersible platform for offshore wind turbine in CFD using OpenFOAM. In the previous videos, I showed how to create the required geometry from these drawings in Salome, and I show how to create the computational mesh in Snappy Hex Mesh, the mesh generator of OpenFOAM. And in this video, I will show you how to uh, choose the solver and how to prepare the steps required for this solver. So namely, how to prepare the boundary conditions, how to prepare the physical properties, and um, dynamic mesh. So let's go ahead and see it. So this is the platform I created, and I'll show you. This is the final product of today's work. We already had our mesh, and today I will explain you how to create the required boundary conditions for different simulations and how to set up the waterline. Before doing these, we need to choose the proper solver. Okay, so OpenFOAM has different major solvers, especially for ocean engineers or naval architects. And most of the go-to solver is interFoam. It has volume of fluid VOM solver to compute the free surface, and therefore it can very well simulate the waves and the free surface and such effects. So in this tutorial, we will use this interFoam solver, and I use OpenFOAM 2206, and you can use any ESI versions OpenFOAM OpenFOAMs like 1806 or 1812. It should have 4 digits, and if you use these versions, if you choose Open interFoam, you don't need to choose its variants like interDynFoam or something like this, and to use the dynamic mesh. If we just set up the dynamic mesh, and interFoam will already automatically reach the dynamic mesh and provides the dynamic mesh ability. So we need to check the required boundary conditions, and these are the boundary conditions for the inlet. Okay, so to make an easier image, so this is the inlet and this is the outlet. So actually these are very similar, and you can choose any side to be inlet or outlet. And but this the first simulation I want to do is the free oscillation, where the our floating structure will only simulate oscillates due to its own weight. Like if we uh, drop it from the air to the water, and it will oscillate up and down, and slowly the oscillations will decay out. So I want to do this first before adding the waves. So these inlets or outlets are almost meaningless, because there will be no inlet, no flow coming in or out of the domain. So, and you can assume these to be like um fixed walls, or you can assume to be these to be like symmetry or even zero gradient, which means uh, you can just rely on the solver to compute these variables automatically, rather than assigning certain boundary conditions. So this is what the zero gradient boundary condition is for. So for the inlet and outlet, I use zero gradients. For the sides, symmetry, because we assume a very wide ocean. And for the top is the tricky part, and it represents our atmosphere. So we need this specific pressure, inlet, outlet, velocity boundary condition, and it should be kept at 0. Okay, and bottom is in this scenario, I assume it has a finite water depth, so there is no slip wall at the bottom. So there is the effect of the certain water depth. Okay, if you want to assume like very deep waters, you can choose this bottom to be symmetry. And for the float, the float means our floating structure, and it should be moving wall velocity. Because we will use we will be using the free decay, and we will be using the dynamic mesh functionality. So our structure will move. It means our wall will move. So we need this specific moving wall velocity. Okay, for the pressures, everything is fixed to be fixed flux pressure. This is a special uh, pressure boundary conditions developed for in OpenFOAM to deal with especially with these free surface flows, and you can put almost everywhere except the top. The top is an atmosphere, so the atmosphere pressure should be 0. So I mean this is the 0 reference pressure. Okay. For the symmetry, we need to put symmetry for every boundary conditions. Okay. And for we have these two phases, alpha air and water, and alpha water boundary conditions means uh, we need to set the boundary conditions for our inlets and outlets, whether our inlet is made of water, the incoming flow is of water or air. We need to define it. So this alpha water is for this purpose, and for the inlets and outlets, we can have both zero gradients, because we cannot decide whether it's coming water is coming in or out of the domain. Okay, because it's not a problem yet. And for the top, again, the atmosphere is the most important part we need to care about in these in VOF simulations. And for top, it's inlet outlet boundary conditions, and the inlet value should be 0. So I will check this file. I need to check the U, P minus RGH and alpha. I will not care about the turbulence for now. Okay. So this is a U, and inlets, outlets, and bottom, and the top is pressure inlet outlet velocity, and float, which is our turbine platform, with moving wall velocity. The sides are symmetric. Okay, and for the P minus RGH, this is P minus RGH. Now it means rho GH. Okay, this is basically the dynamic pressure without the hydrostatic pressure. Okay, and here as I mentioned, I put fixed flux pressure for everywhere except the top, which is a total pressure, and except the sides, which is already a symmetry. Okay, and for the L4 water, the inlets and the rest are 0 gradients, and the top is inlet and outlet, and inlet value should be 0 because 0 means air, and if you put 1, we have very physically impossible simulations. Okay, so we need to keep like this. Okay, and yeah, we have symmetry for the sides. So you may notice that the order of these boundaries are different between each files, because I have been a bit reckless about the order, and it doesn't matter because as long as you uh, properly care about these curly brackets, you will be fine. Okay, so we are good with the boundary conditions for our flow variables. So another one we need to care about is this point displacement boundary conditions. Okay, and all we need to care about is this float, which is our moving structure, our wind turbine foundation, wind turbine platform, and it should be set at calculated. So it means the boundary of this structure or these points will be moved by the solver, and the motion will be calculated. Okay, if you made a mistake, like you put like fixed value or uniform fixed value, you will face very disappointing results. Okay, because the structure will not move, and a wall, this moving wall, will not move, and the mesh around the meshes around this wall will move, so it will diverge very soon. Okay, I made this stupid mistake. This is a very stupid mistake, and I made it, and I mm, I thought, oh, what's wrong with my simulation? It's a very stupid mistake, but you can easily avoid it. Okay, and for the sides, of course, we have symmetry, and for every other single patches, we only need fixed value. So it means other patches, other walls, inlets, outlets, top, bottom will not move. So this dot asterisk means everything. So in OpenFOAM will prioritize our uh, named boundary conditions first, and this will be all. It means all except these, so it means every other things will be fixed. Okay, so we have finished our boundary conditions. Okay, and the next step is to adjust the water depth. Okay, so this is the water depth of the working condition. I copied this from the NREL website, and I already wrote a disclaimer about this, and I just copied just for demonstration, and the copyright belongs to totally to the respective owners. Okay, so this is this diagram, and you can see the still water depth is 26 meters, and it means it's uh 10 meters from the top of this. So I made a few hand calculations, and based on this guy's position, you can easily do it if you wish. Okay, so sources search. I will need to extract first. First, I will extract this guy. Float. Okay, just no. Okay. I'm sorry. Okay, so now we have this our structure, and we can see the x, y, and z ranges. So z is from -6 to 26, etc. And so it means from -6. So this is a zero line, 0 and -6 to 26. So if I put like here, it will be okay. Okay, so all we need to do is like to put the the depth or the z-axis z coordinate of this uh, water level to be 26. Okay, so it's an easy calculations. You can easily do it by hand, and the important part is to make it happen, and you can do it in here. No. Oh, sorry, I didn't do it that I mean this guy is 10. So the idea is to create a box and fill that box with water. So this file sets field x, mean it will set the field values of certain region with certain values. Okay, so what it does is we have our alpha water file, right? So it will fill this file with our desired fields. Okay, so here I instructed to make a box ranging this from a very large box, but the important thing is it's up to 10 meters in z direction, so around here, and fill it with water. Okay, you may say the the sorry, you may say the real depth should be 26 meters, but why 10 meters? So this is an oscillation free oscillation test. So it's like you drop this structure to the water, so it's not fully stabilized yet. So I purposely kept the depth to be 10. Okay, so it will oscillate up and down. Okay, so in this test I will use this 10 meters, and you can run it. So we have covered the boundary conditions, and the next step is setting up the dynamic mesh. So I will use 6 of motion, rigid body motion, and this is an old slide, so you may neglect it, but the idea is the same, and you will have mass and spring and a damper, and we will uh, adjust these in the dynamic mesh dictionary. So where is the dynamic mesh dictionary? It's inside this constant directory. So this is the dynamic mesh, and these are, you can just neglect. Okay. So if you open the dynamic mesh dict, this is what we get. So you can just copy these, and the important parts are here, and we need to name the patches, which is our float. It's a very simple name for my this offshore wind turbine foundation, and these inner distance and outer distance means it will it will create like a circle, a sphere, two spheres maybe, okay, and a diameter 10 meters and 40 meters. So the mesh inside these will not move, so you need to adjust this, but generally the inner distance may be 0 to something, and the outer distance may be something a little bit bigger, and you will be fine. Okay, and center of mass. So where do we get this center of mass and mass of inertias? So that's why I needed to rely on this NREL document. So I have the data. Okay. So the document says the overall tower mass is like this, etc. So the platform mass, including the ballast, is here. Okay, so you put this value directly to this mass, and the center of mass is here. The center of mass location below stationary water level is 13.46 meters, and you can do some calculations, and on my coordinate system it's 0.54 meters. Believe me, I already hand calculated. Okay, and for the moment of inertias, we have already have these data, so this will be used. So this and this, okay, and 3 will be used. Okay, so roll, pitch and yaw, roll, pitch and yaw. Okay, so if you have these 3 data properly, your simulation will do fine. And for the acceleration relaxation, we can just relax the acceleration, and if you do not want relaxation, you can do it 1.0, and the acceleration will be at full swings. So the simulation stability may be a little bit affected, so I decreased a bit for more stability, but in results it should be similar. Okay, and this guy need to be 1, so this acceleration should not be dumped, at least for this simulation, because our simulation is about the free oscillation, in other words, free decay. So the decay will be due to the uh, water viscosity, and we don't have any other dampings defined, even not the structural dampings. So this damping should be 1. So if you put like something smaller than 0, like 1, like 0.1, sorry, 0.9 or something, our we will have under overdamped result. Okay. And solver, we can choose Newmark, Crank, Nicholson, etc. And for the constraints, I didn't choose anything. You can choose an constraint. It means that you can choose certain directions of motion, and you can choose to connect some imaginary springs and dampers. So I assume no uh, spring and no damping, so just do not use these. Okay, okay, and you will be able to run it. Okay, so all you need to do is to copy your this no inflow boundary conditions to here in your to your zero directory, and set the water level by typing set fields. Okay, and then after that you can run by interFoam and it will run. Okay, uh, actually I don't want to spend time on running, so I will stop the video here, and in the next video I will show you how to set up the wave boundary conditions for uh, this structure, and I will show you how to analyze the results. Thank you very much.